everyone. Myself Priyanka, and my room number was 24011A0533. And my teacher was Raju sir, who was working as an assistant professor in Tripoli department. And today's my presentation is about ideal transformer. So first of all, what is a transformer? A transformer is an electrical device that changes the voltage of an alternating current using the electromagnetic induction. It consisting of two coils of wire called the primary coil and the secondary coil, wound around a common core. So here this is a core, and this is the primary winding, and this is the secondary winding. When an alternating current flows through the primary coil, it creates a change in magnetic field around it. This magnetic field induces a voltage in the secondary coil. The voltage induced in the secondary coil depends upon the ratio of number of turns of the in the primary and the secondary coils. So this is the coming to the key points in the transformer. Voltage transformation. Transformers can either step up or step down the voltage. If the secondary coil has more turns than the primary, then the voltage is step up. If the secondary coil has fewer turns, then the voltage is step down. So in a step down transformer, the number of turns in the primary coil are greater than the number of turns in the secondary coil. So it creates a step down voltage. Now, in the step up transformer, the number of turns in the primary coil are less than the number of turns in the secondary coil. So it creates a step up voltage. And coming to the power transformer, in an ideal transformer, the power is conserved. The power entering the primary coil is equal to the power existing in the secondary coil. The power is the product of the voltage and the current. So if the voltage is transformed, the current is inversely transformed. Applications of a transformer. Transformers are used in many areas such as power transmission, where they adjust the voltage to reduce the energy loss over the long distance, and in the various electrical devices to regulate the voltage supplies. So then what is an ideal transformer? An ideal transformer is a theoretical model used to understand how transformers works without considering real-world losses or inefficiencies. So in an ideal transformer, the following assumptions are made. No losses. So there are no energy losses due to the heat, resistance, or magnetic leakage. This means that electrical energy supplied to the primary coil is transformed to the secondary coil without any losses. And there is a perfect magnetic coupling. The magnetic field generated by the primary coil perfectly links to the secondary coil, meaning that all the magnetic flux produced by the primary coil is used to induce voltage in the secondary coil. No resistance in the coil. The wire used for the primary and the secondary are assumed to have no resistance. So there are no losses due to the resistance of the winding. And then no core losses. The core material of the transformer doesn't produce any losses like eddy currents and then hysteresis, which takes place in the real transformer. Now, in an ideal transformer, the input power to the primary coil, the power input to the primary coil is exactly equal to the power output from the secondary coil. This means that the product of voltage and the current on the primary side is same as the product on the secondary side. Maintaining the power conservation. The voltage and the current ratios are determined by the ratio of number of turns in the primary to the secondary coil. So let us understand it mathematically. So in an ideal transformer, the following relations takes place. So the voltage across the primary is equal to the number of turns in the primary coil into the rate of change of flux, whereas the voltage across the secondary coil is equal to the number of turns in the secondary coil to the rate of change of flux. By taking the ratio of the above two equations, we get voltage across primary by voltage across secondary is equal to number of turns of primary by number of turns of secondary. So in an ideal transformer, as we discussed, that input power equal to output power, which is nothing but the product of voltage and current across the primary is equal to the product of voltage and the current across secondary. Both are equal. So the ratio, from this we get a ratio called voltage across the primary by voltage across the secondary is equal to the current, secondary current by primary current. So from the above two relations, we conclude that voltage across primary by voltage across secondary is equal to number of turns by primary by number of turns by secondary, which is equal to secondary current by primary current. So this is the relation that we observe in the ideal transformer. Now, let us discuss about the efficiency of an ideal transformer. The efficiency of transformer is nothing but the ratio of output to the input power expressed as a percentage. So the efficiency equal to the output by input into 100. So output of power by input of power into 100. So what is an output power? Power delivered to the secondary coil is nothing but the output power, and the input power is nothing but the power supplied to the primary coil. So in an ideal transformer, since there are no losses, so the input power is always equal to the output power. By this, we get the efficiency of an ideal transformer is 100%. But for a real transformer, it is not 100%. Okay. So let us discuss about the applications of an ideal transformer. The first thing is the power transmission. Step-up transformers increases the voltage for long-distance transmission, reducing the energy losses. Step-down transformers reduces the voltage for the safe use in homes and industries. Now, electrical isolation. Transformers provide electrical isolation, ensuring safety, protection from voltage surges. Voltage regulation, used in the devices like chargers, UPS systems, and power supplies to adjust the voltage for specific needs. Electrical motors and welding machines. So transformers supply the current voltage for the motors, equipment, and then like welding machines. High frequency applications. In telecommunications and electronics, transformers are used for signal transformation and modulation. So then power supplies. Transformers converts the voltage in an AC or DC converters and switching the power supplies for the devices like computers and consumer electronics. So then let us discuss about what is the difference between this ideal transformer and the real transformer. First, coming to the energy losses. In an ideal transformer, there are no losses. Okay, all the power supplied to the input coil is transformed to the secondary coil. But in a real transformer, the losses occur, like due to the welding, core losses takes place, and leakage of flux is also taking place. And then efficiency. In an ideal transformer, as we discussed, there is a 100% efficiency. But in a real transformer, the efficiency is not 100% due to the aforementioned losses. Like typically in a real transformers, like the efficiency is of 94% to 99% efficient. Then magnetic coupling. In an ideal transformer, perfect magnetic coupling between the primary and the secondary coil takes place. As the magnetic flux produced by the primary coil links with the secondary coil, real transformer, imperfect magnetic coupling takes place because some magnetic flux doesn't link with the secondary coil, resulting in the leakage flux. And coming to the core losses, in an ideal transformer, no core losses takes place. That is nothing but no hysteresis or eddy currents. But in a real transformer, core losses occur due to the magnetic properties of the core material, causing energy dissipation in the form of heat. Voltage and current transformation. In an ideal transformer, the voltage and the current are perfectly transformed based upon the turns ratio, with no losses affecting the transformation. But in a real transformer, the voltage and the current transformation is affected by losses. And the actual voltage or the current may differ slightly from the ideal due to the factors like resistance, imperfect coupling. When coming to the size and the cost, in an ideal transformer, since it is a theoretical model, it doesn't account for real world material, design, construction. But a real transformer are built with the physical materials and their size and the cost depend upon the design, voltage rating, and the efficiency of the transformer. Then, what are the limitations of this ideal transformer? That is, first thing is that no energy losses. Means assuming the 100% efficiency, but in a real transformer, they have a losses. Perfect magnetic coupling. All flux is assumed to link, but some flux leaks. No resistance in coil. No copper losses in ideal transformer, but real ones do. No core losses, assuming no energy dissipation in the core, but real transformers have core losses. No load regulation, assumes constant but transformer experience voltage drop under the load. Infinite bandwidth, works at all frequencies, but real transformer have some frequency limits. No physical constraints, ignore size and cooling which are required in a real transformer. As we assume there is a linear core material, but in a real transformer can saturate. So in an ideal transformer, there is no saturation, but in a real transformer, it will saturate. Then I'm concluding my topic with that ideal transformers are a theoretical model with no losses and 100% efficiency, but real transformers experiences losses like copper, core, etc., and have efficiency limitations. And the applications of these ideal transformers are they guide real transformer design for power transmission and voltage regulation. And the key takeaway, while real transformers aren't perfect, ideal transformers provide a foundation for understanding and designing them. Thank you.